Hello, good morning, students. In the series of NCERT solutions, I completed till exercise 5.6 in previous class. So today we will discuss exercise 5.7. So watch it carefully till end, and if you like it, please share it with your friends. So come to the exercise 5.7. In this, question number 1 is find the second order derivative of the function. So second order derivative, what is second order derivative? As we calculate dy upon dx, that is the first order derivative. So whatever you get, you again differentiate it. Okay, you have to differentiate it 2 times, then it is called second order derivative. If you differentiate the same function 3 times, then it is called third order derivative, and so on. So if you want to calculate second order derivative, nothing is new. It's very simple. Like in this, is y is given this much. You differentiate it once. So you will get it is equal to differentiation of x square is 2x, 3x is 3 only, and differentiation of 2 is 0. So your dy upon dx is 2x plus 3. Now again differentiate it. This side we will write it as d2y upon dx2. d2y upon dx2. It is a symbol. d2y upon dx2 is a symbol. Okay, you have to consider it as a symbol like dy upon dx, and again differentiating it, we'll write d over dx of dy over dx. So it is not written as d square y upon d square x square. No, it is written as d2y upon dx2. Its meaning is you are differentiating y with respect to x 2 times. All right. So it is d2y upon dx2, that is second order derivative. So again differentiating both the sides. d2y upon dx2 sometimes is also written as y2. Sometimes it is also written as y double dash. Sometimes it is also written as f double dash x. That is called d2y upon dx2. So you have to differentiate it twice, that's all. So in once we got this much as dy upon dx, again differentiating it, you will get d2y upon dx2 is differentiation of 2x plus 3. So differentiation of 2x plus differentiation of 3. So differentiation of 2x will be 2 only, and 3 is 0. That's all. Like x raised to power 20. So x raised to power 20, one time you will differentiate, it will become 20 into x raised to power 19. That is dy upon dx. You again differentiate it. So it will become 20. Now you have to differentiate x raised to power 19. That is 19 into x raised to power 18. That's all. That will be d2y upon dx2. Now we come to the question number 3. So questions are very simple. Nothing is new in this. X cos x. You have to differentiate x cos x. So once you have to differentiate it using the product rule, first you differentiate x cos x as product rule. So cos x as it is, derivative of x. Now x as it is, and derivative of cos x. So the derivative of this x is 1. Derivative of cos x is minus sin x. So first derivative is cos x minus x sin x. Now you again differentiate this cos x minus x sin x. That is the second derivative. So we will differentiate cos x and then x sin x by the product rule. So derivative of cos x is minus sin x, and now you have to differentiate x sin x. So sin x as it is, differentiation of x, plus x as it is, differentiation of sin x. We are using product rule. So the differentiation of this x is 1, and differentiation of this sin x is cos x. In this way we will get the second derivative. You have to differentiate log x. So once a differentiation of log x will be 1 upon x, and again differentiate it. The differentiation of 1 upon x, it is actually x raised to power minus 1. So minus 1 into x raised to power minus 2. That will be minus 1 upon x square is second derivative. Find second order derivative of x cube log x. So we differentiate it using product rule. So product rule, your first function as it is, that is x cube, log x as it is, differentiation of x cube, plus x cube as it is, differentiation of log x. Differentiation of x cube is 3x square, and log x is 1 upon x. So you get it is log x into 3x square plus x square. You again differentiate it to get the double derivative. So to differentiate it, I have taken x square as common. So this is 3 log x plus 1. Now to differentiate it again, we'll use the product rule. So d over dx of this thing is 1 plus 3 log x as it is derivative of x square as it is derivative of 1 plus log 3x. Derivative of x square is 2x. 1 plus 3 log x means derivative of 1 is 0. 3 log x is 3 upon x. Like e raised to power x sine 5x. You have to differentiate it. Again, use the product rule. First one, sine 5x as it is derivative of ex, then ex as it is derivative of sine 5x. So it is sine 5x, derivative of ex is ex only. It is ex, derivative of sine 5x is cos 5x into 5. Cos 5x, then differentiation of 5x, that is 5. So this is the first derivative. You have to again differentiate it using the same product rule. So to get second derivative, again differentiate this. So in this sine 5x plus 5 cos 5x as it is derivative of ex. Now ex as it is and derivative of this thing. So derivative of ex is ex. So we'll put the value of this at this place. Now you differentiate this. So differentiation of sine 5x will be the cos 5x into 5. You can write it directly. 5 cos 5x will be minus 25 sine 5x. So in this way we can have the second derivative of this also. Question number 7 is just similar. E raised to power 6x cos 3x. So e raised to power 6x cos 3x. So cos 3x as it is derivative of e raised to power 6x. Then e raised to power 6x as it is derivative of cos 3x. Derivative of e raised to power 6x will be e raised to power 6x into 6. And derivative of cos 3x will be minus sin 3x into 3. So this is the first derivative. Again differentiate it to get the second derivative. So d over dx of this whole thing. Again we will differentiate these both the part of this using the product rule. So first one is 6 as it is. This 6 is as it is. We will differentiate this e raised to power 6x cos 3x. In this minus 3 is as it is. We will differentiate this thing. So this will be differentiated by product rule. In product rule, differentiation of e raised to power 6x is 6 e raised to power 6x cos 3x as it is. Then e raised to power 6x as it is, derivative of cos 3x will be minus 3 sin 3x. In the same way, we will do this also. Sin 3x as it is, derivative of e raised to power 6x. Then e raised to power 6x as it is, derivative of sin 3x. So derivative of e raised to power 6x is 6 e raised to power 6x and sin 3x is 3 cos 3x. And in this way, we will get the answer. You can further simplify it. Question number 8, find the second derivative of the function tan inverse x. So first derivative of function tan inverse x is 1 upon 1 plus x square, and derivative of 1 upon 1 plus x square, you can use the chain rule. First it is 1 plus x square raised to power minus 1. So how will you solve it? It is 1 plus x square raised to power minus 1. So its differentiation will be minus 1 into 1 plus x square raised to power minus 2. And then you have to differentiate 1 plus x square also using the chain rule. 1 plus x square raised to power minus 1 will be the minus 1. 1 plus x square raised to power minus 2. And using chain rule, we will differentiate 1 plus x square. And that will be 2x. Alright. Now log of log x. So first derivative will be by chain rule. Differentiation of log x will be first as a log x, you will get 1 upon log x, and then you have to differentiate log x also. So it is 1 upon x log x, that can be written as x log x raised to power minus 1. We have to redifferentiate it to get the d2y upon dx2. So first you will differentiate it as something raised to power minus 1. So it will be minus 1 into this thing raised to power minus 2. Again we have to differentiate x log x. So x log x we will differentiate using the product rule. So log x as it is differentiation of x as it is differentiation of log x. Now differentiation of x is 1 and log x is 1 by x. In this way we will get the answer. Question number 10. They all are very simple questions. Sine of log x. So first you will differentiate it as a sin x. So that will be cos of log x, and then you have to differentiate log x, that is 1 upon x. So it is cos of log x divided by x. This will differentiate using the product rule or quotient rule. So denominator as it is, differentiation of numerator, minus numerator as it is, differentiation of denominator. Over here you have to differentiate cos of log x, that will be minus sine of log x first as a cos theta, and differentiation of log x. In this, differentiation of x is 1. So the differentiation of this log x is 1 upon x, and in this way your second derivative is over. Question number 11. So 11 question you just see. In this we have to prove something. We have to prove d2y upon dx2 plus y equal to 0. So y is given 5 cos x minus 3 sin x. So naturally you have to find d2y upon dx2 means second derivative. Then only we can get this as the answer. So take this as one equation. Now differentiate it once. 5 cos x minus 3 sin x. It will be minus 5 sin x minus 3 cos x. Okay, negative sign you have taken common. You redifferentiate this thing. So again differentiating this, you will get the same minus y, means it is minus of 5 cos x minus 3 sin x, and 5 cos x minus 3 sin x was minus y, because initially y is given 5 cos x minus 3 sin x. So you replace this by y, and d2y upon dx2 is equal to, you will get it is minus 1. So you change over this minus y, this side it will become d2y upon dx2 plus y equal to 0. Question number 12, y is equal to cos inverse x, find d2y upon dx2 in terms of y. Okay, so y is equal to, given cos inverse x, you differentiate it once, you will get it is minus 1 upon 1 minus x square, that can be written as minus 1 minus x square raised to power minus half. Again we will differentiate it to get the second derivative. We will differentiate this. First we will differentiate it as minus 1 minus x square raised to power minus half. So it will be minus half into 1 minus x square raised to power minus 3 by 2. Then you differentiate 1 minus x square, and it is minus 2x. So ultimately you get it is minus x upon under root of 1 minus x square whole cube d2y upon dx2. Alright, it is under root of 1 minus x square whole cube. Now what will you do? You want to get its answer in terms of y. So y equal to cos inverse x initially is given. So on the basis of that you can write x equal to cos y. So in this expression you replace all x by cos y. So d2y upon dx2 is minus cos y upon under root of 1 minus cos square y whole cube. 1 minus cos square y is sin square y. So it is sin square y whole cube. So sin square y whole cube is nothing, square root is also there, so it is sin cube y, it will be there outside. Because this is overall sin raised to power 6y. So it is minus cos y sin y into 1 upon sin square y we can write, that is minus cos y into cosec square y. Question number 13. So in question number 13, y is given something and you have to prove x square y2 plus xy1 plus y0. Here y2 means d2y upon dx2, y1 means dy upon dx. So this question will do easily. First y is given, so you have to find the y1. So to get y1 you differentiate this. 3 into d over dx of cos of log x plus 4 into d over dx of sin of log x. Differentiation of cos of log x will be minus sin of log x, and then you have to differentiate log x also, that would be 1 by x. Similar way, differentiation of sin of log x will be cos of log x, and then we will differentiate this log x, it will be 1 upon x. So we will have it is minus 3 sin of log x plus 4 cos of log x, and in denominator there will be x. Alright. Beyond that, Now in both in denominator x is there. So I will solve this by some another method. You can take help from this PDF which I have done over here. I will take cross over this x to this side. I will write it as xy1 is equal to minus 3 log x sine of log x plus 4 cos of log x. You differentiate this again. In this you have to use the product rule. So what will you do? First, differentiating throughout. Derivative of x is 1, y1 as it is, plus. Now x is as it is, or derivative of y1 will be y2. Y1 means derivative of dy upon dx. If you will take, it will be d2y upon dx2. Right side, come to the right side now. Minus 3 sine of log x. It will be minus 3 cos of log x, and then derivative of log x, that will be 1 upon x. 4 cos of log x. So cos of log x, it will be minus sine of log x divided by x. Derivative of log x also. So in right side you see x is the LCM. Right side x is LCM. Okay. So I will change over that to the left side x LCM. So I will multiply this whole equation by x both the sides. So see what will happen. I will multiply this whole equation by x. So in left side it will be xy1 plus x square y2, and right side we are left with this x is not there, this x is also not there, so you just see it is only minus y. Whatever is left is minus y. This is minus y only. If I take negative sign as common, and this thing 3 cos log x plus 4 sin x is actually equal to y, so it is equal to minus y only. So I get xy1 plus x square y2 plus y equal to 0. That you have to prove. So by this method, you just note it down and you will get your answer easily. Don't follow this PDF method which I have given over here. Follow the method which I have just explained. Okay. So in this way you will get the answer. Come to the question number 14, 1-4. Y is equal to e raised to power mx plus b into e raised to power nx. Something want to prove. So first you get dy upon dx. Differentiate it a as it is e raised to power mx. Derivative of e raised to power mx will be m into e raised to power mx. Derivative of e raised to power nx will be n into e raised to power nx. So we will again differentiate it. Redifferentiate it. It will be am as it is differentiation of e raised to power mx. Bn as it is differentiation of e raised to power nx. So this will be again m into e raised to power mx. So it will become am square into e raised to power mx. This is n into e raised to power nx. So it will become bn square into e raised to power nx. You have to prove d2y upon dx2 is equal to this plus this. In this question, you just substitute the values of d2y upon dx2, dy upon dx, and y, and at last you will, on solving it, you will get it is equal to 0. So in this question, you have to find dy upon dx, you have to find d2y upon dx2, and finally substitute the values. Question number 15 is very simple. You need not to substitute anything in question number 15. You see y is equal to 500 into e raised to power 7x and 600 into e raised to power minus 7x is given. You just get first one dy upon dx. I am writing it as y1. So it will be the 3500 into e raised to power 7x minus 4200 e raised to power minus 7x. Alright, that is the y1. Now you get y2. So you again multiply it, differentiate it. So it will be 3500, or you can write it as 7 into 500. So it will be the 7 into 7 into 500 Again, the derivative of this is 7 into e raised to power 7x. So I have taken it as, to differentiate this. So minus, it is 600 into 7 is already there. I have to differentiate e raised to power minus 7x again. So that will be minus 7 into e raised to power minus 7x. Alright. You just take this 49 as common. In this 49 is there. In this 49 is there. So we will take 49 as common. So y2 will become 49. On taking common, you will get 500 into e raised to power 7x plus minus plus 600 into e raised to power minus 7x. And that is y only. That is y only. So in this case, we will get y2 is equal to 49y. Over here also it is done in the same way. So you can take help from here also. Question number 16. If e raised to power y into x plus 1 is equal to 1, show that d2y upon dx2 is equal to dy upon dx whole square. Alright, d2y upon dx2 is equal to dy upon dx whole square. It's quite simple. Like it is taken e raised to power x, y into x plus 1 is 1. So e raised to power y is equal to 1 upon x plus 1. Taking log both the sides. Left side it will come y log e, and y log e is actually y only. Y log e. Log e is 1, so it is y only. Alright. So y log e is equal to log of 1 upon x plus 1. Change over the sides. Differentiate this. Log of 1 upon x plus 1. Log of 1 upon x plus 1. You differentiate this, it will be reciprocal of this. That will be x plus 1 into differentiation of 1 upon x plus 1. That will be minus 1 upon x plus 1 whole square. So this will be cancelled out by this. So ultimately we will have only minus 1 upon x plus 1. We will have only minus 1 upon x plus 1. That will be the derivative of this. So dy upon dx is minus 1 upon x plus 1. Again differentiate it. So 1 upon x plus 1, its derivative will be minus 1 upon x plus 1 whole square. So overall derivative will be 1 upon x plus 1 whole square. So this 1 upon x plus 1 whole square can be written as minus 1 upon x plus 1 whole square. We can write it like this. And dy upon dx is given minus 1 upon x plus 1 whole square. This is given equal to minus 1 upon x plus 1 whole square. This can be written as minus 1 upon x plus 1 whole square, which I have mentioned in this step. So you can write d2y upon dx2 is equal to dy upon dx whole square. Question number 17 is y equal to tan inverse x whole square, and you have to prove whatever is this given. So first differentiate it. So tan inverse x whole square means 2 tan inverse x, and d over dx of tan inverse x. D over dx of tan inverse x will be 1 upon 1 plus x square. You just cross multiply 1 plus x square. So it is 1 plus x square y1 is equal to 2 tan inverse x. Again differentiate it. So left side you have to use the product rule. 1 plus x square is one function, y1 is second function. So 1 plus x square as it is, differentiation of y1 will be y2. Y1 means dy upon dx. If we will differentiate it, we will get d2y upon dx2. Then this y1 as it is, and differentiation of 1 plus x square, that will be equal to 2x. Okay, this we will differentiate by product rule. First this is as it is, derivative of this. Then y1 as it is, derivative of 1 plus x square is 2x. And right side it is 2 upon 1 plus x square. You just cross multiply by this 1 plus x square and you will get the answer. So in this way, your exercise 5.7 is over. Few questions of miscellaneous are left, so I will explain those also in this class. Earlier, I have explained most of the questions of miscellaneous. So come to the question number 17 of miscellaneous. Till 16 I explained earlier. The 17th question is nothing, it is x is equal to a cos t plus t sin t and y is equal to a into sin t minus t cos t. You have to find d2y upon dx2. d2y upon dx2. First we will find dy upon dx. So this is parametric form. In parametric form we will find dy upon dx. First you get dx upon dt. So this a is as it is derivative of cos t plus t sin t. So first we will differentiate cos t, that will be minus sin t. Then we will differentiate t sin t by product rule. So sin t as it is differentiation of t will be 1. T as it is differentiation of sin t will be cos t. So this sin t is cancelled out by this sin t. So it will be at cos t is dx by dt. Similarly, we will differentiate this y with respect to t. So a as it is derivative of sin t minus t cos t. So differentiation of this sin t will be cos t and t cos t will differentiate using product rule. So cos t as it is derivative of t plus t as it is derivative of cos t. Derivative of t is 1, so it will be cos t only, and derivative of cos t will be minus sin t, so it will be minus t sin t. On just opening the bracket, this cos t will cancel out this cos t, so we'll get at sin t, that is dy upon dt. So to get dy upon dx, you will write dy upon dt divided by dx by dt. So we will divide dy upon dt by dx by dt. dy upon dt is at sin t and dx by dt is at cos t, so it is tan t only. This is dy upon dx. Now, it's a very important step. Most of the students commit mistakes in this step. So note it down, it's important one. To get double derivative, now what you have to do? You will differentiate this dy upon dx with respect to x. This side you will differentiate this t with respect to x. Tan t with respect to x. So take care, its derivative will be sec square t. But you have to write dt by dx along with this because we are differentiating function of t with respect to x. In this we are differentiating function of t with respect to x. So you have differentiated it as sec square t, but you have to also write dt by dx. Two type of mistakes generally student commits in this one particular question. What will they do if they are asked to find d2y upon dx2? First, they will find d2y upon dt2 from here and d2x by dt2 from first function, and they divide both of them. That is absolutely wrong method. Second one, if you get dy upon dx, it's okay. We'll again differentiate it to get d2y upon dx2. But while differentiating, you have to take care of this thing that dy upon dx we get in terms of t. When we'll again differentiate this with respect to x, don't forget to write dt by dx. This is the most important step in this. Generally, students forget to write this dt by ds and they simply write d2y upon dx2 is equal to sec squared t. So take care of this step. Now you just put the value of this dt by dx in this that you calculated in this step, that is a t cos t. On replacing the value of dt by dx, whatever comes is the answer of this question. Okay, question number 18. Fx is modulus of x whole cube is given. Show that f double dash exists for all real values of x and find it. So we know that modulus of x is equal to plus x if x is greater than 0, greater than equal to 0, and modulus of x is minus x if x is less than equal to 0. It is not possible to differentiate or integrate the modulus function. You have to break it into the actual value, real value function. Okay, so fx we will take separately for all values for which x is greater than equal to 0. we will take fx is equal to plus x cube, because x is equal to modulus of x is x only. In this you just differentiate. Once you will get 3x square and twice it will be equal to f double dash x you take, it is equal to 6x. That part is over. When x is less than 0, for those values you will take modulus of x cube will be equal to minus x cube. Modulus of x cube will be minus x cube. Why? Because modulus of x is equal to minus x when x is less than 0. So f dash x will be minus 3x square, and again differentiate this. F double dash x will be minus 6x. So we'll have f double dash x for values x greater than equal to 0, it is equal to 6x, and less than 0, it is equal to minus 6x. Means it is defined everywhere. Alright. Next is the question number 19. It is based on the principle of mathematical induction, that is PMI. In first step, we know that in PMI we will check it for n equal to 1. d over dx of x raised to power n. By principle of mathematical induction, we have to prove it is n into x raised to power n minus 1. So put n equal to 1 both the sides. So in left side you will have d over dx of x. In right side it will be n means 1 into x raised to power 1 minus 1. So dx by dx, this is 1, and right side also it is 1. So we can say P1 is true. It is P1 is true, okay? Now let Pk be true, we will assume. This is the method. In principle of mathematical induction, we will prove P1 is true, then we will let Pk be true, and then we will prove that Pk plus 1 is also true. If all these three steps are followed, then we can say it is true for all the natural numbers. So first P1 we have proved it is true. Let Pk be true. So to write Pk, what will you do? In this whole expression, you replace n by k. So d over dx of x raised to power k is k into x raised to power k minus 1. Now we have to prove that Pk plus 1 is also true. So find Pk plus 1. What will you do? In this expression, replace n by k plus 1. So left side it will be d over dx of x raised to power k plus 1. And right side you have to prove it is equal to k into x raised to power k. K plus 1 into x raised to power k. It is k plus 1 into x raised to power k you have to prove. So what will you do? I have taken it as d over dx of x raised to power k plus 1. You break it as d over dx of x into x raised to power k. So apply the product rule. X raised to power k as it is differentiation of x. X as it is differentiation of x raised to power k. This is 1. And this, using the property, this one property, you replace d over dx of x raised to power k as k into x raised to power k minus 1. You replace this thing because it is, we have let it is true that d over dx of x raised to power k is equal to k into x raised to power k minus 1. So I have replaced this by k into x raised to power k minus 1. So this is x raised to power k minus 1 into x. That becomes x raised to power k. So it is k into x raised to power k. From both these two, you can take x raised to power k as common. It will become k plus 1 into x raised to power k. And that can be written as k plus 1 into x raised to power k plus 1 minus 1. The x raised to power k can be written as k plus 1 minus 1. Thereby your pk plus 1 statement also becomes true. It is also true. So now it is true for all the natural numbers. It is true for all the natural numbers. Question number 20. It is given that using the fact that sin A plus B, sin A cos B plus cos A sin B, and the differentiation obtain the sum formula for cosine. So sin A plus B, sin A cos B plus cos A sin B, we know, differentiating this both sides with respect to x. So I've just written d over dx. So now differentiation of sin A plus B will be cos A plus B. You have to also differentiate a plus b. In this, we'll use the product rule. First, cos b as it is, differentiation of sin a. Now sin a as it is, differentiation of cos b, this thing. In this also, we'll use the product rule. Sin b as it is, differentiation of cos a. And now cos a as it is, differentiation of sin b. So it is cos of a plus b, d over dx of a plus b equal to, you see right side, it is cos b. Differentiation of this will be the sin a, cos a, and you have to write dA by dx. The sin a as it is, its differentiation will be minus sin b, and you will write dB by dx. The sin b as it is, differentiation of cos a is minus sin a, and you have to write dA by dx. Cos a as it is cos b dB by dx. Now what will you do? The left side it is cos a plus b dA by dx plus dB by dx. Right side cos a cos b minus sin a sin b dA by dx plus dB by dx. Actually cos a cos b is into dA by dx plus cos a cos b into dB by dx. Similarly minus sin a sin b dA by dx minus sin a sin b dB by dx. So we can take this thing as common. So this is cancelled out both sides. So we'll have cos a plus b is equal to cos a cos b minus sin a sin b. Okay, in this step you may get confused. Need not to get confused. Actually cos a cos b is multiplied with both dA by dx plus dB by dx. Okay. Similarly minus sin a sin b is also multiplied by both dA by dx plus dB by dx. That is why I have taken this common in single step. You can take it in 2 steps also. Now this is a determinant, and you have to find dy upon dx using this determinant. Y is given equal to this much, and you have to prove this much. So it's quite simple. You just expand the determinant. So we expand this determinant, fx into mc minus nb minus gx into this, and now you differentiate it. I've expanded it and differentiated. Left side is dy over dx, differentiation of this plus differentiation of this plus differentiation of this. So this is a number, it is as it is. Differentiation of fx will be f dash x. In this is a number, and differentiation of gx will be g dash x. And this is a number, and differentiation of hx will be h dash x. Now you re-represent this in the form of determinants. Okay, on re-representing in the form of determinant, it will come equal to this much only. Okay, because you see f dash x into mc minus nb, it is the same thing. mc minus nb. G dash x into lc minus na, you just see g dash x, it is lc minus na, plus h dash x lb minus ma. And I give you a different trick how to differentiate a determinant if only variable is there. Variable means function of x is there in only one row or column. You just differentiate that row or column, that's all. Like in this case, these ALMN and ABC are constant, FA, GB and NC are variables. So to get dy upon dx, you just differentiate these 3 terms, that's all. As I proved in this one particular case, I've expanded determinant, and then I got this one as the answer, and this thing is actually equal to this determinant. So ultimately what is the change? On differentiating this, only these 3 variables are differentiated. That's all. So in this way, now your differentiation is over. In one topic is there in this, that is exercise 5.8, and that belongs to Rawls theorem. So Rawls theorem I will take separately. So I hope now you will be able to solve all the questions of NCERT. Thank you.